Okay, this example will consist of doing a proof with couples or ordered pairs basically. The reason for that is because I'm seeing the little cross symbol here and I'm crossing A with B intersect C. So there are two sets basically being crossed, so that means we're going to have ordered pairs. And similarly, A cross B, that's an ordered pair. A cross C is an ordered pair. Then I'm taking the intersection, which means I'm going to get ordered pairs. So this is going to be a long proof. It's not very difficult. It's just a tedious proof. And I'm going to start the same way as usual. Let A, B, C be any sets. And once I let A, B, C be any sets, there are basically two proofs I'm going to do. One of them is going to be proving that A cross B and C is a subset. And the other one is going to be proving that A cross B intersected with A cross C is a subset. So I'm going to go this direction first. Okay, so proof of 1, I guess. All right, so let the x comma y ordered pair be an element of A crossed B intersect C. Okay, remember the A cross B and C gives me ordered pairs. That's why I'm choosing x comma y. Now, by definition of the intersection, by definition of cross, I know that the x element is going to be inside of A, and at the same time, I know that the element y comes from B intersect C. Now, let's talk a little bit about this B intersect C over here. Having y be an intersection means that y will come from the first set and from the second set. So far, I know that x comes from A, and I know that y comes from B, and also y comes from C. Okay, how do I know this? By definition of intersection. Okay, so I can break the and apart, or I can put it together as an intersection. However, this means at this point we can say that x is inside of A and y is inside of B. So x comma y is inside of A crossed with B as an ordered pair. And saying that x is in A and y is in C allows me to say that x comma y is also an element of A cross C. But this implies, by the same definition of intersection, having and in the middle means we can kind of like join them together and say that x comma y is an element of A cross B intersect A cross C. This is again by definition of the word intersection. And that's the end of proof 1. So QED 1, and this is the end of proof 1. So to recap, what happened in proof number 1? Here's what happened. First of all, we saw that we are working with A cross B intersect C, and because there's one cross right there, that tells me that the elements are ordered pairs. This is why I said let xy be an element of the cross. Now, by definition of the word cross, I can say that the x first number in the order pair comes from A, and I can also say that the second element y comes from the second set, which is B intersect C. But now, since B intersect C is an intersection, I can basically break it apart, and I could separate the B by itself and the C by itself, and y still belongs in both of them. And still, as usual, x is inside of A. But having that x be in A and y be in B and y be in C, I can do a combo of x, y together, and I could do a combo of x comma y together like that. And that's kind of what I did on the next line. I took xy from A cross B, so this is the same cross that we're talking about from the start, and this is another cross from the start also. Okay, but since x comma y is in A cross B, and it's also in the A cross C, we can take those two sets and put them together and use the intersection. And now we have proven that if you're part of this, then you're automatically part of the right-hand side of the equation. Now, we're going to do the other direction this time. We're going to be doing proof 2. So what's happening in proof 2 is this. We're going to start with the element being on the right side of the equation, and we're going to show that it's an element of the left side of the equation. So we're going to start with let xy again be an element of the A cross B intersected with A cross C. Then, by definition of the intersection, we can break the xy apart and say that it belongs in A cross B, and at the same time it belongs in the A cross C. Okay, so again, what am I doing here is this. I'm taking this intersection symbol and I'm breaking it apart as I can with the definition. Now, saying that x comma y is in A cross B means that x is in A and y is in B. So I'm going to focus on the first term right here and break that one apart. So this means x is in A and y is in B. Again, how do I know this? I know this by the definition of the cross. And at the same time, if I focus on the second set, or the second x comma y, then I will be able to say that x is in A, and at the same time, I can say that y is inside of C. Okay, again, how do I know this? I know this by the definition of the cross product. Okay, now there's a lot of ands in here, so here's what I'm going to do. I'm going to collect a couple of them together. Finally, I can say this. I can say that x comma y is where? So it belongs inside of A, for sure, because x comes from A, crossed with B intersect C. Remember, y is in B and y is in C, so y is in the intersection of both of them, especially because there's ands everywhere. And the x belongs in A, regardless. So, as an OR pair, the x comma y belongs in A crossed B intersection C. So this shows that if you start with A cross B, intersected with A cross C, then you'll be a subset of A crossed B intersection with C. And this is the end of proof 2. Okay, so let's finalize it. Since in part 1 we said this, and in part 2 we said this, then this would imply the equality. Then we have equality. And this is the end of the proof. So QED.